bit microcontroller. Sometimes it varies from semester to semester. Sometimes we go 16-bit microcontroller, but we use it as a case study to apply the different theoretical concepts we will have learned through the theoretical part of things. So that's how the subject goes. We go with the theory that we take. We learn, of course, theoretical, advanced theoretical concepts of hardware design or computer system design, and we apply them through a case study of a microcontroller in this case. Yeah, so that's more or less the structure of it. So on the practical side, the subject will look very much more like embedded system, meaning microcontroller programming, but a microcontroller programming with a different approach, definitely, from what you guys learned in Digital Systems 3. So a bit more advanced. And then on the theoretical side, we'll study concepts that are related to the hardware design of computer systems, basically. I'm not sure how many of you, which one of you actually works in the embedded type of environment? Anyone? It might be possible.
No.
Network?
No, me, I'm more in software.
Ah, you're more in software. Okay.
Yeah.
Yeah, and Noreditse?
Same here. For me, it's more...
Computer engineer is both, eh?
Sorry.
Yeah. Computer engineer
I'm also
both. But yeah, opportunities, we work where we get opportunity, of course.
Yes.
So now let's start with some basic discussions around the study guide, basically. I just got given this module. I taught it in 2019, but then I got given back to me. So I'm actually in the process of updating the study guide, of which I'll send to you today still after I've finalized that, but that will be after class though. But in terms of what the content of it is, it's very clear to me. First of all, I need to present myself. I'll share my screen quickly. Okay. I think by now you can be able to see my whiteboard.
Yeah, it's loading.
Okay.
Still loading.
Yeah. Oh, still.
Yeah.
Give it some time. Okay.
I'm not seeing anything yet. I don't know.
Still.
Are you seeing something?
Okay. What about?
No, it's black. It's just black.
Oh, that's weird. Let me redo. Stop sharing. Share again. Now. Also check on my phone.
Still nothing.
Oh, that's awkward.
Oh yeah, now it's loading.
Okay.
Yeah. Now we see the whiteboard.
Okay. So, Emmanuel Migabo. You can call me Migabo. It's fine. My first name is Emmanuel. My email address is Migabo MEZA. Okay. Well, my cell phone number you have, which is also on WhatsApp. But I've also linked my work number now to my cell phone. Yeah, of course. So that is my TUT number, which means you can also join me through it. You can join me. You feel free to WhatsApp me for consultation. I don't mind that. It's mostly virtual consultation unless we have something we are building and we really need to meet. We'll be going on campuses on such occasions. We'll be going on campuses when we have the projects or any practical session, but also when we have to have assessments. Okay. Test in particular, assignments and so on we can do from home. Consultations can be done via WhatsApp, can be requested via WhatsApp, but can be done through Teams. And we'll be using the same class link. Whenever we've agreed for a consultation session, we'll use the class link and we'll meet them through Teams and discuss. Okay, so that's about me. Okay, then we move into the subject itself. We have, in terms of prescribed textbook, in terms of the prescribed textbook, we use a textbook called The Architecture of Computer Hardware and System Software and Information Technology Approach. That is our textbook. And a third edition is fine. I'll share a copy with you. You don't have to buy one. So I'll share a copy with you. Those are the offers. Okay. So that is the textbook we use. As I mentioned, I'll share a soft copy with you so that you don't have to necessarily buy one. That is mostly gonna guide us through the theory part, of course. Okay, so that is about the prescribed textbook. Okay, I want to also speak about. Let me clear the canvas. Yeah, I also want to speak about assessments. We obviously will have assignments. I try to do 3. We do one after every 2 units, and we have class tests. We have what we call formative tests. When it comes to formative tests, we do 2 of them. When it comes to class tests, we do 1. We also have, of course, nowadays, you know, we speak about summative tests in case we go continuous assessment. There's a bit of clarity that I'm still seeking with respect to this. But because right now there are 2 terminating modes, you can either go exam or summative. So what the arrangement is that the subject that was summative in first semester remains summative in second, and the one that was exam remains exam. From what I pick up, but that's subject to confirmation, and I'll confirm that quickly, is that this is still summative test. I mean, it's continuous evaluation terminating mode. In terms of summative, we normally have 1, but we have a sick one or missed one. In case you didn't do the first one, but I also use it as some form of makeup to help those who didn't do well in the main one. In terms of marks allocation, before I forget actually, then there's a practical side. The practical side is summarized in a project. Project which is global, takes more or less the content of the entire module into account, but we do it as we go. So when we cover units related to subsystems of that project, we handle them. And by the time we get to the end, we integrate the entire thing and we submit. So in terms of marks allocation, as you all well know, the summative test is 40% of final mark. That's more or less across board. When it comes to the project, it's the one that takes the next biggest amount of marks. I give it 25% normally. And for formative tests, there are 2 of them. They're each 10%, making it 20. Then we've got the assignments and the class test. In fact, I think considering the fact that the semester is quite short, we'll just do 2 assignments and 1 class test, or 3 assignments. So we'll do 3 assessments in the end. That is what I'm trying to say. It will be either 3 assignments once, or 1 class test and 2 assignments. In either case, it's gonna be 5% each, forming the 15% remaining. Is that okay?
Yes, sir. Maybe
Sounds fair, right?
yeah, or maybe we could consider even 3 assignments, but the third one being optional to make up for anyone who did not do well.
Well, I'm struggling. You are fading. Your voice is fading. Just to speak up a bit.
Can you hear me now?
Yes, I can.
No, I'm saying we could maybe possibly do 3, but then the third one out of the assignments is just a makeup one if one of the 2 was not well done.
Yeah, that's a good point. Yeah, we could go up to 3. Yes, I agree. We go up to 3.
Yeah, I also agree with that.
Okay, that's fine. Yeah, we can go up to 3. Which means, well, the subject is practical in by nature, but when I speak about, if we go 3, I might have what I call practical assignment, meaning it will be the type where you actually do by simulation a practical task or a practical problem. You solve it by simulation. Yeah. Speaking of practicals, because that next thing we discuss now, I want to speak about the practical aspect of things. What microcontroller are we going to use? What softwares and tools that you need to install? I just want to go to here to the lab manual. Okay, so now, yeah, so we will use Kale. I'm sure most of you know Kale from Digital Systems 3. Tell me, was Digital Systems 3 optional or compulsory?
I think it was, if I remember correctly, it was compulsory.
Yeah, I think so. In computer system, it should be compulsory. Yeah. So yeah, you used Kale Microvision back then. It's a Kale Microvision development kit. We're using the same, but it's a newer version of it, of course, version 5. So you need to download, and this is after class, of course, download and install that MDK on that link. I'll provide you with this lab manual. There's no license needed or any key of any form. You also need to download the legacy support from Kale. Okay. And this is important for Cortex-M devices because the device we'll use will be a Cortex-M device. Okay, so if I go onto those links, allow, what it might use, it might end up using Internet Explorer. Let me just copy the link instead. Okay, so if I go, yeah, so that will just be our IDE, Integrated Development Environment, just for you guys are software, so you understand better, of course. You understand very well. So we also, of course, include some version control, especially for the project. One must not just show ability to write firmware that works, but also the entire, more or less, to a certain degree, the software engineering part of things must be demonstrated throughout the project and reported upon. So you're keeping track of the different versions. Most of you, I'm sure, use Git. Am I correct? Hello? What version control do you use?
Oh, sorry. I use GitHub. I was on mute.
Okay.
So I do some PowerShell programming for Windows servers. So on the version control using GitHub Enterprise.
GitHub, okay. And
Yeah.
it's back end you do.
Pardon?
Do you do back end or front end?
No, there's no backend. So this is just for automating manual processes using Windows PowerShell. So I'm a Windows Server engineer.
Okay. Sorry, I didn't hear you properly. Okay,
Yeah.
that's fine.
Yeah.
So sir, I deal a lot with APIs. So I normally use GitHub as well, and Postman, and Swagger.
Okay. All right. We will use in this subject in the embedded world. After you've downloaded the IDE, of course, in the embedded world, one of the most common thing is called source tree, but it's just a plugin for GitHub. So it's Git actually, but we use it through source tree. So you'll download and install the Kale MDK 5 on the link that I'll provide in the lab manual. You will download and install source tree, which is just a front end app for Git. It's Git, but if you want, but no, for reporting sake, and uniformity, let all get source tree. That's not a problem, and set it up. Because I was about to say you could use also Git in a console, which is fine, but because we'll be using this as part of the reporting in terms of the project, so let's just stick to, for uniformity's sake, to source tree, which is just calling Git in the background. It's just some visual GUI application for using Git. Okay, so we can proceed, and then you get the legacy part. Now, when it comes to hardware, we normally buy development boards. I've tried to get few development boards, especially because you guys are just two, right? Am I correct? You are two only so far, but according to my registration list, you could go up to 5, which means 4 are registered, 1 has got the intention to register. Let me see. Yeah, right now in class we are just 2. Yeah, so it should be possible for the department to get us these boards for practicals, and because you are only 2, I can actually hand the boards to you, and you can keep them home instead of coming to the lab and so on. Meaning, and because well, it's just the microcontroller programming, so you don't need necessarily a lot of equipment. Unless we are doing some timing aspect or anything like that. Okay, but normally we have a dev kit we use for this, and that will be I'll show you which dev kit I'm talking about. For practicals of this subject, we use this dev kit. In the worst case scenario, in case the department doesn't buy the dev kit, then we will do simulations, which is also okay. We'll go by simulation approach. So it's the Nucleo 64 microcontroller. It's a 64 microcontroller, 64-bit microcontroller. That's how the board looks like. I personally have one, but yeah, if in fact, yeah, I have my own. I'll get the department to buy 2, and then I can issue them. We can meet and I can give them to you. Okay, but also for logistical aspects, which side of Gauteng do you live in?
I'm based in Midrand, but soon I'll be moving to. I'll be based in Hartbeespoort. So, yeah.
I see. Okay. The reason I'm asking that is that with the previous classes, sometimes I'll make an arrangement and we'll have some assessment in main campus instead of Soshanguve. I don't mind that personally, and I'm always able to make that type of arrangement. But of course, I always need to make sure it suits better everybody. Rather, you get the point. Yeah. Okay.
Okay. No, yeah, I think that we can arrange, going forward, because I'm also gonna be based in Montana, from next month.
Okay, Montana is kind of in the middle. Okay, but it's okay. So yeah, so that is the dev board we'll use for this. We can get some technical data sheets document for it. We need them basically. We have a data brief. and we need a user manual, of course. Okay, the data sheet of the actual microcontroller on top, which is a ST microcontroller, is also easy to get, and you just have to use the part number of the microcontroller and you get the data sheet. The 64 STM32, actually, sorry, the STM32 microcontroller, but we need to know the actual part number in full. That is STM32F 401 RET 6U. So that's the what one would normally Google to get the full data sheet of the actual microcontroller on top of the board, which is more important. Although it's part of a dev board, what we are interested in mostly is the actual microcontroller on it. The dev board is just to give us some other peripheral access. It's an ARM processor, by the way, and we specifically chose an ARM processor because that is what is one of the most popular microcontroller types that we have used in industry nowadays. Okay, so that is some of the documents that you'll need, of course, for as we go along. We have also a simulation, as I mentioned, simulation platform that we can use as an alternative to the board itself. We have another link there that speaks about the setup. That's fine. So now to enable download debugging features, because as you do firmware development or any form of hardware design through firmware, you normally need to debug sometimes to ensure that the processes, what you wrote in code is what you expect, the outcomes you are getting is what you expect. And this is very important, especially with microcontrollers, as you have very limited visuals. So debugging is very important. So for you to be able to debug, you'll need to also download download the nuclear firmware on this link and install it. And some more information about debugging approach when it comes to this board are given here. Of course, as we go along, we'll have a session where I'll show you how to do the debugging and all of that. Okay. So now, how does the project development go? The IDE, which is Microvision, as I mentioned, is what we use. You'll normally open that and create a new project. Okay, you name it the way you want to. You choose the target. Let me see. I've got Microvision installed on my side already. Although you guys are yet to install it. I have Kale. Wait for it to open. But basically, this lab manual takes you step by step as for how you set up a project. Okay, and well, then the rest is ensuring the generation of X file is important because that is what the image we load in the end in the microcontroller. The rest of adding source code files, as well as header files and libraries that we will use as we go along. Now, when it comes to debugger, we use the ST-Link debugger. That will be the actual hardware debugger that you connect on the board as you do debugging. Yeah, so we set it up by means of a serial wire and a serial port. And yeah, we'll go through this in more details as we get to the practical. I just wanted to let you know about which platform we are using or platforms we are using for the practical side of the subject. Are there any questions with respect to that? No? Pretty clear?
Yes, we are.
Okay, so I'll share this document with you, of course. What I expect from you before next week is to have done all the setups. I hope you all have computers. I would assume so, actually. Yeah, normally this problem.
I've got a computer, but I'm using a Macintosh.
Yes.
So I don't know if it will work on a Macintosh. Is it gonna work on a Mac?
Yes, there is a microvision for Mac as well.
Ah, thank you. Thank you.
Get a version for Mac. Yeah, that's fine. But worst case scenario, are you in a position to set up some VM or?
Yeah, that's what I normally do with other subjects. If there is if like some software, if they want the Windows strictly, I use I've got some VMs on the cloud that I use.
Perfect. Okay.
Yeah.
At least you've got a plan. Okay. If it doesn't work, but normally, as far as I know, there is a macOS version for Kate. Okay. So that's about it in terms of the general brief about the module. The simulation platform, as I mentioned earlier on, well, there's a way to do it by debugging, but that won't give you all the peripheral access and so on. An actual live simulator would be Proteus. We can use Proteus in this case. I'll just have to get the license set up, and I'll share that with you. And once I do, and but my approach will be as follows: I'll investigate first the ability to have the boards. If I do have them, I'll contact you. We'll meet, and I'll hand them over to you. Then, if I don't get the boards, then I'll revert quickly to the simulation software, in which case I'll give you the setup and the license key. Is that okay?
Yeah, that's okay, sir.
Okay, perfect. Okay, so if there are no further questions, we can jump into the subject itself, starting with Unit 1, of course. Okay, okay, so Unit 1 is actually corresponding to Chapter 1 of the textbook, the prescribed textbook. And yeah, it speaks about computer systems in general. It's more to just set up the background of computing. I mean, of a computer is seen as a system in general, and it speaks about the architecture, the memory organization, etc. So each time we'll map this to the memory organization and architecture on the microcontroller we are using, the STM microcontroller we are using, just to relate the practical side to the theory side. Okay. But to start, we have, pardon, apology for that. Yeah. To start, we have to speak about the internal structure of a computer, but this first slide is just saying, basically, in essence, how where we come from in terms of computing, of which this is history, and you've done this through many subjects. It's just to say computers are becoming more and more faster in terms of processing. We have, because you are BTech and the next step is postgraduate, I also have to, of course, bring in some elements of research and actuality. We have more and more another big computer migration nowadays, which is migration towards the virtual computing. And this is happening across board, not only on personal computing, but not only on personal computing level, but even at lower layers, at communication type of systems. We are seeing more and more some form of virtual switches, virtual gateways, etc. So more and more processing is shifted towards the cloud, and localized computer systems are just handling mostly sensing and data acquisition. Okay, that's a brief about the current trends in computing, and it's just a fast changing environment. That is what this slide is just trying to say there. Sorry. Computer is a bit slow. Why is it important to study computer architecture? At a user point of view, it helps understand system capabilities and limitations. Be it a microcontroller, be it a personal computer, be it a server, be it a mainframe even. You, as a user, you need to understand the architecture of the computer system so that you can be able to know what is capable of doing and what is not capable of doing at a user point of view. Secondly, it's very important for making informed decisions, and this is broad. It's broad in a sense that informed decisions can be at different layers and in different job tasks. For example, at the developer point of view, that will allow you to, because you know the architecture of your computer system and the limitations and capabilities, you can actually plan better your software development. At the administrator point of view, you can allocate better resources, etc. So the making of informed decisions is applicable to different users differently, depending on their job task. Okay, so it also helps the user improve communications with the information technology professionals, in a sense that the user who might not be an IT personnel, if they can be able to understand the computer architecture, then they can engage better with their IT support. And that's more, the third bullet is more oriented towards support. When it comes to a system analyst, knowing the computer architecture allows them to conduct surveys, determine feasibility, and define the document user requirements whenever they are analyzing, because they're analyzing a system or planning for any form of design. It also helps them specify computer systems to meet application requirements. And of course, lastly, at the programmer level, it helps create efficient application software for specific processing needs, because not all applications are necessarily efficient, and that efficiency is one aspect we bring in this module on top of just functionality. And the efficiency can be in terms of memory utilization, can be in terms of processing time, and many other aspects. System administrator, as I mentioned earlier, owner manager, knowing the computer architecture helps them install, configure, maintain, and upgrade computer systems, maximize system availability, optimize system performance, ensure system security, small resource allocation and management. When it comes to a web designer, optimize customer accessibility to web services, system administration of web servers, select appropriate data formats, design efficient web pages, for example. So now, before I move on to the IPO model, I want to say, because we went and chose as a case study for this subject a mini computer, so we would technically add a bullet here in our case as far as we are concerned in computer systems, and that will be for a firmware developer. To a certain extent, there's a lot of similarity with the programmer, what we call programmer in one of the bullets there. But there are also some specifics that, specific aspects that are reserved or reserved to the firmware developer when it comes to the knowledge of the computer architecture benefits. Anyone who can think of any? Of course, as I mentioned, a firmware is also a programmer, so efficient use of efficient writing of efficient applications is one. So writing of efficient firmware applications in this case. And when we speak about efficiency, as I mentioned, it's memory, it's processing time. Any other thing you can think of for a firmware developer, what will be specific to them? that the knowledge of the computer architecture or the architecture of the computer they are using would bring as benefit. Any one of you? No one. You've forgotten.
Yeah, sorry, say I've got flu. For me, it's been some time. It's been some time since I did like this kind of work.
Okay.
Yeah.
Okay. Yeah, that's the purpose of this first chapter, is really to refresh as well your mind. So when it comes to firmware developer, it's actually critical to know the architecture of the mini computer in this case, which is the microcontroller, because then, for example, because for what reason is it critical? It's critical because as a firmware developer, we are closer to machine language. So we write code, we access memory registers, both what we call general purpose general purpose registers that we often refer to in short as GPRs, as well as special function registers, SFRs, directly. So you wouldn't, for example, for the case of special function register, access any register for configuring, for example, serial communication or timers or counters. You wouldn't access it directly if you don't know at what address it sits. Yes, we do have translation libraries, but that we can make use of, and that will allow us to use special function registers by their names, because someone else has actually mapped them to their addresses for us. So we'll pull that header file or that library, and then we can start using the names of the special function registers instead of the actual address, but addresses. But when it comes to assembly or inherently, whether assembly or C, inherently, you suppose as a firmware developer to access memory by its address. And accessing memory by its address then definitely require you to know the architecture of the mini computer or the microcontroller in this case, because then you need that will allow you to know how much memory you have available in terms of ROM and RAM, as well as flash memory, of course. But in general, let me just say, in terms of program memory and data memory, you need to know exactly how much you have available, and which part of memory is byte addressable, for example, or bit addressable. And that all of that you know through the computer architecture, because if you don't know the computer architecture, the architecture of your microcontroller, you wouldn't know a specific register is only bit addressable and not byte addressable, for example. So that's one of the benefits that the knowledge of the computer architecture brings when it comes to a firmware developer in particular. Okay. Added to this is the timing aspect. The timing aspect of the microcontroller or of the computer system is very critical, and you only know that through knowing the architecture of the clock system. I'll call it clock system of the microcontroller or of the computer. And when I'm calling it a system because with modern microcontrollers or modern computers in general and modern microcontrollers in particular, you don't just feed them with a single, you still feed them with a single external clock, but they have internally a full clock division and clock routing module, so that you can get from the same reference clock multiple clocks at different speeds. Okay, and that is where I want to focus for now. If we go back to I want to take the datasheet of the microcontroller we are using, the STM. Okay, so that I can use that as an example, but I'll speak in general, but we also apply it to this specific microcontroller. I just want to explain the timing aspect, because the timing aspect is very critical for any hardware design concept, because the entire timing within a computer system is governed by means of a clock, and it starts there. That is where electronics meets computer system in this case. Okay. I'm just trying to see STM 32L476. 476 VGTX. Okay, so I'll just get its data sheet. But we also obviously have the clock description on here. We can already take it from here because the dev board is having the same microcontroller. So it said here that we have a crystal oscillator of 32,768 kilohertz on board. External SMP, I'm looking at the 24 megahertz high-speed clock, which is also another possible clock to enable. But the main clock is the crystal oscillator in this case, and it's the 32.768 kilohertz. And there's a specific reason why microcontrollers most of times use this type of crystal oscillator. Because one would be wondering, why does it have to be 32,768? Why wouldn't it be 32 kilohertz or 33 kilohertz? Okay. Okay, I see someone lost connection. Okay, that's fine. Hopefully he will connect again. But so that's the clock frequency we are working with. But I just want to go into the timing aspect here. So you've got a microcontroller, and as part of the features or functionality of the microcontroller, you have timing. And of course, timing governs anything from delays that you might need. In microcontroller processes and functions, you sometimes need delays. You might have delays, you might have clock generations. So this is the part where you learn about generating a clock, for example, on a peripheral of the microcontroller. And the generation of a clock can be used for many hardware design applications, such as ringing a buzzer or anything that needs a digital clock to operate. Okay, you've got delays, clock generation, and any other type of delays. I think is a global word in a sense because it takes into account timing in general. But lastly, timing is very important for communication, serial communication, because with serial communication, as you know very well, data is transferred 1 bit at a time. Because data is transferred 1 bit at a time, that on its own, as I said, 1 bit at a time simply shows that it involves time. There needs to be a mechanism at the microcontroller level to keep track of the speed at which the data is being transferred, which we call the baud rate. And that can only be done from the reference component, which is the clock in this case. And in this case, the reference signal, which is the clock is the reference digital signal in the microcontroller for timing operations. The clock, in this case, we've chosen to use a crystal clock. For this specific microcontroller is 32,768 kilohertz. Okay, that's not so that is on one hand the hardware part, which is the clock and the microcontroller device through which the clock is read, of course, and configured. And on the software or firmware development point of view, we've got timing as the in terms of applications. We've got delays, we've got clock generation, we've got serial communication, etc. So now, what is the relationship between a clock and the different functionalities, timing functionalities, as I've mentioned them? I'm not sure Murandeni has rejoined the meeting. Ah, there he is. Okay, so he's back. Okay. Oops, lost him again. Yeah, it's gone again. Okay. Yeah, luckily there's a recording, but the idea is that in any computer system, we've got a reference clock. On your computers, sometimes when you go, if it's Windows, you right click on the computer name and you say properties, you get to see what reference clock it's using. And the clock influences the performance, the overall performance of the computer, especially in terms of processing. Here I'm talking about processing performance. So we normally have the oscillating frequency, okay, of the clock of the computer system, from which, of course, we can work out what is the oscillating period, which will be 1 over the oscillating frequency. And that tells us the duration after which the clock repeats itself, of course, because that is period by definition. Now, when it comes to processing from the CPU within the microcontroller, because of course a microcontroller, being a computer, like any computer system, must have a CPU, central processing unit, which itself is form of an ALU, arithmetic logic unit, and a control unit. The ALU is in charge of performing the operations. Computing operations are by nature arithmetic and logical. So it's either logical operations or arithmetic operations. So those are the type of operations that are handled in a computer system in essence. The rest of operations, such as sending an email, sinusoidal operation, cosine, logarithmic, they all can be brought down to arithmetic and logical operations. Within the category of arithmetic operations, of course, you know the basic ones: addition, subtraction, division, multiplication. And in the category of logic operations, the category of logic operations, we've got ending, ORing, and inverting or noting, basically, as the basic logic operations. And from there, of course, you've got derived logic operations, which include your these include your XORing, NOR, NAND, etc. And you can go complex for you can go as complex as you can by forming what we call logic expressions. And all of this is something we revise in this subject in chapter 3, whereby we speak about digital systems in general as a revision. Okay, so now the point is that going back to here, we've got a clock, which is often an external crystal that is running permanently, and we have its oscillating period as the base of timing within a computer system. Now, the execution by the microcontroller through its CPU of any instruction is measured in what we call machine cycles. As you know very well, instructions on a computer system are processes to a certain degree. They are made up of cycles. For example, reading from memory has got the following processes, if I can mention them. You would normally load the address of where you want to read from on the address bus. You will issue, there is a fetch instruction that is issued, and there's a retrieve instruction from the memory, there is decoding of the address to identify which address we are trying to access. There is the data is copied from that address within memory onto the data bus, sent back to the CPU, where it performs a a retrieve cycle. So fetch and retrieve cycle coupled with the other in between processes form couple of cycles that govern the sorry, let me admit him. Couple of cycles that govern the operation. They form couple of cycles that govern the operation of the execution of an instruction. Sorry. So we call machine cycles. We assess or we quantify the duration of the execution of instruction on a computer system by means of what we call machine cycles. Now, for every every computer system hardware designed, there is always a fixed relationship between between the machine cycle and the number of clock periods it takes to execute. So we always told one machine cycle is equal to how many clock pulses. Okay. So for example, for the PIC 16F you used in digital systems 2 back in the time, one machine cycle was equal to 4 clock pulses. For the AT51 microcontroller you used in digital systems 3, which is an ARM processor as well, you had 12 clock pulses per machine cycle. Now, the next, in this subject we are studying with the STM microcontroller we are using, STM32 microcontroller we are using, we need to get from the data sheet how many clock pulses one machine cycle is. Okay. Let me just go to the data sheet. MC. Okay. You need normally the actual data sheet. So to go to the actual data sheet. At the end of the day, we need the actual data sheet or the user manual. Maybe will give us that. Yeah, but data sheet definitely. Yeah, let's go to the data sheet instead. The actual microcontroller from this family of microcontrollers that we are using is we are using a STM32. There it is. Okay, so STM32 L6 no L6VGT. Okay, the X part is just to say it could be 2, it could be 3, and so on. Okay, it's the data sheet we are after. Okay. Okay. No, that's way too many things. You see in the summary part. Clock sources 4 to 48 megahertz crystal. That is what it can handle. We've got a 52 kilohertz for the real-time clock. We've got an internal clock of 16 megahertz. We've got an internal low power clock of 52 kilohertz. We've got 3-phase locked loops. Yeah. 16 timers. Okay, let me just see. They're not speaking about how many clock passes we have per machine cycle. You can always retrieve that. But while we find out that, okay. Okay, we'll find out that, but let's carry on with the principle. So normally you have one machine cycle you'll be told it corresponds to, let's say, X clock pulses, which means one cycle of the CPU execution will take that long. So if you go from an oscillating clock, for example, of 16 megahertz, just as an example, that means the oscillating period is 1/16 times 10 to the power 6 seconds. And that will be 1/16 microseconds. How much is that? That can be computed as 1 divided by 16. So we're talking about 62.5 nanoseconds for one clock pulse. Sorry. So if one machine cycle takes, let's say, 12 oscillating periods, that will be 12 times 62.5 nanoseconds, and that will be that times 12, and that will give times 10 to the power. Okay, 62.5 times 12. Yeah. So that gives me 750 nanoseconds per machine cycle. So most of the times what happens is that an extra layer on top of this is that the execution of the basic instructions, and I'm saying basic because some other instructions can be seen as complex because they are a combination of a couple of instructions. The execution of some basic instructions is normally measured in terms of, sorry. Yeah, the execution of basic instructions of the microcontroller, of which every microcontroller or any computer system for that matter has got a set of basic instructions. So for all of those basic instructions, their execution is evaluated in terms of number of machine cycles they take to execute. So if a specific instruction, maybe addition of two numbers, if I go assembly, or even if I do it in C, it's still the same. If addition of two numbers takes 3 machine cycles to execute, and this is normally disclosed in the datasheet of the microcontroller, then to calculate how long it will take to execute in terms of actual time, you now say it will take 3 times the duration of one machine cycle, which in this case we computed to be 750, and that at 16 megahertz, that will be 3 times 750 nanoseconds. So then addition in that case on this specific computer system, on this specific microcontroller, would take a total of 2.250 microseconds. So what is the relationship between the clock and the duration of execution? Let's look at that. As you can clearly see, is that we have the relationship between the one machine cycle and how many clock passes it entails, which can be translated in X over FOS for depending on the clock frequency at which you are operating. And for Y machine cycle, an instruction that takes Y machine cycles will, in terms of duration, will be Y times X divided by the oscillating frequency, basically. Now, what does that mean? The duration of execution of an instruction on a computer system is inversely proportional to the oscillating frequency of the clock, of the reference clock that is used with this microcontroller, which means the higher the oscillating clock frequency, the shorter the execution of instructions by that computer system. So the higher the clock interface on a computer system, the faster we can execute instruction, the better the processing performance. I hope that's clear for both of you. Is that okay? Are you guys there?
Yeah, no, I'm here.
Okay. Okay. Okay, that being said, I think we can catch a break and resume at 10. You can maybe grab coffee or something in the meantime. I also feel like I need one. Okay, so we resume just now. And
10 o'clock, right?
Yes, 10 o'clock.
Okay, thanks.
Sure.
So do we stay on what's going on with the session?
Pardon? What was the question?
I say, can you hear me?
Yes, I can hear you now.
I was asking, do we stay on or we're gonna join again?
Whichever one.
Okay.
Okay. Okay, thank you. Yeah, I think you've taken the break. So now, after the timing aspect of the computer system and the microcontroller used as a case scenario, as we just did, it's important to look at, sorry, that was one of the criteria, of course, that the knowledge of the architecture of the microcontroller would help with. So we move on to the next topic that is involved in the computer system as well, which is the way we model a computer system. The best way to model a computer system, which is also applicable to many other systems, is actually what we call the IPO model. Input, process, output model. That's exactly how a computer system works. But what does this model consist of? We have the input subsystem, which is made up of anything that is dedicated to bringing data into the computer. So if we speak at a personal computer point of view, this will be your keyboard, mouse, scanner, punch cards, etc. And any form of sensing mechanism, fingerprint reader, card readers, etc. At the processing point of view, the core of processing in a computer system is obviously the CPU, and that is what is in charge of executing the program which is a set of instructions, and these instructions which are fundamentally of two types, arithmetic and logic. That's all type of instructions that a computer can execute. Then we have got the output side, which involves any form of user. I mean, it involves all mechanisms that are used to provide the outcome of processing to the user, either for visualization or for action. So for action, that will be the case of any form of actuation on a microcontroller. Maybe we run a motor or we close a valve. That's actuation. Visualization will be any form of screen and indications, all the way from lower level indications such as LEDs to liquid crystal displays, LCDs, to 7-segment displays, first of all, to liquid crystal displays, all the way to monitors, the way we know them, computer monitors, etc. So that is the output part. But very important, associated with the IPO model, is the storage concept. The storage concept comes in to say processing doesn't go alone. It always goes together with memory. What needs to be stored is twofold on a computer. We store the program itself, which means during execution, the CPU reads it from memory and executes it. We also have to store data, and data can be stored temporarily or permanently, of course. Temporarily, that will be data that we're storing through the RAM memory of the computer, and permanently, that will be data that we store into ROM. So that is the best way to model a computer system, and this model is what we call the IPO model. And that's very applicable to a microcontroller system, of course. And if we have to take the case scenario of our microcontroller system, and we'll jump into more details as we go into the practical side of things, we obviously have a couple of input peripherals to the microcontroller. On the input side, by just reading the brief description of the microcontroller, we can identify which components are actually input components on this microcontroller system. Of course, that is where you have your input-output ports, first of all. That is the most basic you can have. Your IOs, meaning input-output ports. Through that are of two nature. You've got digital ones. So in terms of input, you've got your input-output ports and pins, of course, which can be digital or analog. In modern microcontrollers like the one we are using, you can also have analog inputs. In terms of the input That is mostly the major input interface when it comes to a microcontroller. So you must not confuse input device and input module. The input module is within the microcontroller. The input device is whatever you can interface with the microcontroller. So when you speak about input devices, for example, on a microcontroller, it could be a keypad, it could be something like a keypad, it could be a push button, it could be a switch, it could be a sensor. All of those are input devices. But here I'm talking about the input module within the microcontroller. It's mostly made up of I/O ports and serial ports. The microcontroller we are using also has serial ports. It has got ports for serial communication, of course. So that is the input module, but within the microcontroller. On the outside, in terms of input devices you can interface this microcontroller with, you get a long list. You can have keypads as well. You could have switches, push buttons. You could have sensors. Of course, sensors and their transducer circuits. Yeah, so in terms of the CPU, of course, a microcontroller is a mini computer, so it must have a CPU which is made up of a LU and control unit, as I mentioned. We'll speak about memory just now, which is storage. Let's speak about the output part. In terms of output modules, of course, in terms of output modules, you it still interface through the I/O, the output ports, to be specific. We often refer to them as I/O ports because most of times each of these pins and ports are configurable, can be used sometimes as input, sometimes as output. So it's all configurable. So here we're talking about output ports, those ports that are configured to be output. We also have serial output ports, whether for I2C or SPI, SPI, I2C, UART type of protocols. And besides that, we have, in terms of output ports, I mean output modules, what else can we consider an output module in a microcontroller? We can, okay, by the way, here on the input side, before I forget, the ADC is an input module because it's a port through which the analog data comes in. I mean, it's a module through which the analog data comes in. It's converted to digital format before it's given to the CPU. On the output side, beside the IOs and the serial port, sometimes with certain type of computers, you've got built-in modules that are customized as accelerated hardwares, as we call them, accelerated hardwares. What does it mean, accelerated hardware? An accelerated hardware is a hardware design specific. I mean, it's a hardware module specifically designed to, specifically designed for a specific type of output device. So, for example, you might have a microcontroller with built-in motor driver, for example, and so that module that is internally interfaced with the microcontroller CPU, and that just provides output pins on the microcontroller I/O port for controlling a motor. That internal module will be the accelerated hardware. Okay, we could have an accelerated hardware for CAN bus in vehicular applications, for example. So that will be a piece of hardware within the microcontroller that is dedicated for controlling communication within an automobile, for example. And you get all of these hardware accelerated modules more and more integrated together with the microcontroller, within the microcontroller. But of course, in terms of output devices, because there's module and there's device, I keep on insisting on that. When it comes to output devices, that is where you get your screens, LEDs, all your indicators, LCDs, LEDs, 7-segment displays. This section comprises of any form of actuators. So when it comes to actuators, sometimes they are internal in form of an accelerated hardware, or externally connected as an output device. That will be your motor drivers, for example. You could have your solenoid valves, etc. Those are output devices. Okay. So lastly is the storage part, which speaks to memory. Now, when it comes to memory, the concept of memory at the hardware design point of view, memory of a computer system mathematically can be modeled as a matrix. Memory, the best way to model mathematically the memory of a computer system is to use the matrix representation, whereby you've got columns and rows. Now, when it comes to rows represent what we call addresses. So as you go from row 0, and I'll write it in hexadecimal, depending on how many addresses we have or how big is the memory, you would have a couple of hexadecimal digits. But you go from 0 to a certain number. In this case, that will be 256 addresses, meaning 0 to 255 in terms of address values. Then you have the columns, and the number of columns of a memory device. So columns is what we call the word length. The word length of that memory device. And the word length represents the smallest amount of memory that can be accessed at once. What is the smallest amount of memory you can access at once? And when we say, why do we say this is the smallest amount of memory you can access at once is on a computer system, is that this is the exact size. The number of columns is also corresponding to the exact size of one address. So when your address 00, that's how many cells, as we call them, you can access at the same time. Yeah, I'm mentioning cells already, but the next thing is one element of the matrix representing memory is what we call memory cell. Memory cell. So the number of columns in one specific row is what we call the word length, and that is the minimum amount of cells we can access at the same time. Now, depending on the type of microcontroller at hand, and I will go back to previous microcontrollers you guys have learned. With the AT51, it was an 8-bit microcontroller, which means memory is organized in batches of 8 bits. So in this case, the word length of the AT51 was 8 bits. So it was 1 byte, 1 byte long of 1 byte per address, basically, or 1 byte per row. Now, and I want that being said, and after I've defined what the memory cell is, I just want to ask, Oredite, what would you say now is the size of one cell, memory cell, on the 8051 you've learned, based on the explanation I just provided? Oredite?
I say I'm still trying to figure out. Can you hear me clearly?
Yes, I can.
Yeah. So you want to get the value of the one memory cell based on the word
Yes.
length being 8 bits.
Being 8 bits, yes.
It's a bit tricky for me. I'm not sure.
Okay, it's actually very complicated. If you think about it, word length being 8, that means there are 8 columns.
Yes.
And
starting from 0 to 7, right?
Yes.
Yes.
The fact that it's 8 bits, that means actually every element in that column is 1 bit in size.
Hmm.
And that is a memory cell at the end of the day. You agree?
Yes.
Yeah. So a memory cell here will be a memory of 1 bit. Make sense?
Yes. So in fact, a memory cell is just 1 bit. Right?
It's 1 bit in this specific case.
Yeah.
Okay. So now the microcontroller we are using here is the STM32F. So the 32 part is what shows that this is a 32-bit microcontroller. It's a 32-bit microcontroller. The number of addresses, we'll look at it as we study the architecture of the microcontroller itself. That's number of rows. But because it's a 32-bit microcontroller, that means its word length is 32 bits. Now, there are 2 possible arrangements of when it comes to 32-bit microcontrollers. They could be organized into bytes. So a memory cell of 1 byte each, which would mean then memory cell is of 1 byte, which would mean then there are 4 columns. You get it?
I'm not sure if I follow.
Okay, so if a memory cell of such a microcontroller is 1 byte and the word length we've said is 32 bits. So in other terms, if we tell you that there are 4 columns or word length is 4, so if we ask you for the size of a memory cell, then of course that 32-bit must fit in those 4 columns, which means it is 32 bits divided by 4 per column. Actually per cell, because at the end of the day, it's 1 cell we are looking at in that specific row. You agree? Per cell, which means we've got 8 bits per cell.
Yes.
And 8 bit per cell, that means the memory cell is of 8 bits in this case. You agree? But
yes,
8 bits is what we call a byte.
So I just have one question. How did you deduce or get to the division of 4? I know 32 divided by 4 would give you the 8 bits, but why specifically the 4? Why did you have to divide it into 4 columns? What was the decision or the deal breaker there? I just want to get clarity.
Oh, okay. So no, yeah, it was not a decision. So that leads me actually to memory representation. Normally, when we represent the memory in hardware design, we say, or in general, actually, you would say the number of rows it has. Let's say 40. You say by the number of columns it has. Let's say 4, and then you say the type, if it's ROM or RAM, for example. That's how you would represent a memory device. So here the 4 is a given data. It's not something I came up with. So I had said
it's given.
The same way I can change it.
Got you. Yeah.
You get it?
Yes.
Yeah. So if I say now this device is actually a 32 by 16 ROM or RAM, so what would be the memory cell size? Sorry.
It will be 2 columns then.
Cell size will be how much? Considering, of course, that the word length, which is the number of columns, is still it got no, sorry, the word length is still 32 bits, but we've got 16 columns, as you can see. So the memory cell size will be the size of one cell, which will be in this case 2 bits. You agree?
2. Yes.
Yeah, 2 bits to be specific. You agree? Because there are 6 columns in this case.
Yes.
So that will be 2 bits per cell. You wanted to say?
No, I was agreeing. Sorry, I was agreeing.
Okay, so that's exactly what is going on there. Okay, now of course you know very well that the smallest unit of memory is what we call a bit. Memory. That's what we call a bit. That's the smallest unit of memory. And it stands for binary digits, of course. Which means anything else is a multiple of bits. And in terms of memory organization, I want to draw your attention on this, is that the next grouping of bits we have is what we call a nibble. So whenever we speak about a nibble, you'll know it's a group of 4 bits. Then you've got a byte, which is a group of 8 bits. And from there on, you've got multiples of this, and you can go kilo, let's start with kilobytes, which is abbreviated mostly as KB, megabytes, which is abbreviated as MB, gigabyte, often abbreviated as GB. We have terabytes, often abbreviated as TB. We've got petabytes, which is PB. Now, how many bytes is a kilobyte?
$1,000.
Who was that?
Remember, the K represents 3 zeros, right? Which is 1,000 bytes or 100 bytes.
It's wrong. Let's see what Morandeni thinks.
So how many bytes are in the kilobytes?
Yes.
Kilobytes, right? So bytes, I think it's 1,000.
Yeah, you are both wrong. So in general, a kilo, as you guys are mentioning, is 10 to the power 3 in general, in any other form of measurement. But when it comes to memory units, a kilo is 2 to the power 10, which is 1,024.
Ah, yes.
Let's be careful.
Oh,
yes, it's the 1024.
Okay, yeah, 1024, 2048. Yeah.
Yes.
So it goes in powers of 2. I mean dozens powers of 2, because mega will be 2 to the power 20 now.
Yeah.
Bytes, which you can actually derive by saying a megabyte is a kilo of a kilobyte. So that is 2 to the power 10 times 2 to the power 10 bytes. And that's how we get to 2 to the power 20, which means this will be 2 to the power 50, 2 to the power 40, 2 to the power 50.
This is actually DSY 1. Yeah, we did it in DSY.
But now you must be careful. That's only applicable to bytes. Yes. Because when you go, especially in communication, which is a major application of computer systems, we often go in terms of multiples. Communication measurements in terms of memory go in multiples of bits. Often don't use bytes when it comes to communication. That's where you speak about speed transfer speed, etc., network speed, you know, we express them in kilobytes per second, for example, kilobits, sorry, per second. You can go kilobytes per second if you want, but the kilo when it comes to bits is the same as the kilo when it comes to meters and liters and so on. So when it comes to bits, multiples of bits, being kilobits or megabits, especially mostly used in communication applications. There it's 10 to the power 3, 10 to the power 6, etc. But that's for bits. But when it comes to bytes, it's 2 to the power 10, 2 to the power 20, etc. That's a quick revision there. Is that okay?
Yeah, that's fine.
Okay. So that's in terms of storage. Now, associated with the memory device, which is an array as we've modeled it, are decoders. We normally have a column decoder and a row decoder. And this is at hardware point of view, the way memory is built. Like if you zoom into a computer, you open a computer and you're trying to, you go to memory device of a computer, that it has it's form of an array of memory cells, and you've got decoders interfaced with it. So when an address comes through, of course, the address bus onto a memory to identify which memory row, because the purpose of the when we accessing memory, we're accessing it row by row, meaning address by address. So the address comes through the address bus. It goes first through a row decoder, which is also known for that reason as an address decoder, which then detects, the purpose of it is really to decode what specific row or address we are trying to access. And it's more of a selector in other terms. Then it will select the specific row we are trying to access. Okay. The column decoder, on the other hand, is there for pulling out data out of that specific row that has been selected. That's very important. But now, let's go that in terms of just the next layer after the memory, in terms of hardware design of memory. But now, what about the cell, memory cell? Because the smallest is a bit, how do we design a memory cell of a bit? You've also learned this already. How do you design a memory device that can store up to 1 bit? Anyone? Forgot.
In terms of columns.
No. I'm talking about the hardware design now. You are designing a memory device of 1 bit using electronic components. You forgot.
Through a matrix.
Through a matrix? No. Okay. First of all, we'll look at when it's ROM, meaning flash, etc., and when it's RAM. When it's RAM, a memory unit of 1 bit, meaning you build a device that can, a memory device that can store 1 bit maximum, is a flip-flop. You agree?
Agreed.
The flip-flop can store up to 1 bit. You agree? Let's say whether it's a JK flip-flop, for example, the clock Q and Q bar. Remember, let's say, okay. You remember the operation of a JK flip-flop? No? So if it receives a 1 and a 0, it J is 1 and K is 0, the output will be 1. But that output will remain 1 for as long as the condition on the input hasn't changed on one hand, but also the clock, the new change hasn't been clocked in. So that's why we say it's storing a 1. So whenever you want to store a 1, you would put a 1 there on the input of flip-flop and it will keep that 1. When you change it in a 0, you will put a 0 there and a 1 here, it will keep it in a 0. You agree? So that's how a flip-flop is a RAM memory. I'm saying RAM because when you lose power on a flip-flop, you also lose the data that was stored on its output. Is that okay?
Yeah, that's fine.
And if you go one layer down, you can go, because now we are seeing a flip-flop as an IC, integrated circuit. But if we zoom inside the flip-flop, in terms of hardware design still, we have a flip-flop is actually a combination of logic gates in a certain configuration. You agree? With a feedback configuration.
Yes.
Yeah. And it's often done either in terms of NOR gates or NAND gates. Why those two? Because those are what we call universal logic gates. So if we take that NOR gate implementation, for example, okay, let's go with NOR. We have two NOR gates. It's thanks to the feedback network that we have memory. Because combinations of logic gates with no feedback, meaning nothing taken from the output back to the input, are just what we call combinational logic circuits. They're not memory circuits. They become memory circuit the moment we have feedback from the output to the input, and the moment we add some clock is a gate control, basically. Sorry. We add the clock to control, for extra control, to make sure we control when sorry. So that is a clock, that is maybe J. We control when we decide to pass the value of J by means of a clock. The same clock is used to also control the K inputs. Yeah. As I mentioned, and there's a reason why I mentioned NOR gate, is that NOR or NAND. Because at the logic implementation point of view, these are what we call universal logic gates. Because any other, thanks to De Morgan theorem, which has got two formats, A plus B bar equals to A bar times B bar, A times B bar equals to A bar plus B bar. Thanks to De Morgan's theorem and other rules of Boolean algebra, we can bring any other logic gate to its equivalent in terms of NOR gates only or NAND gates only. Means we use universal logic gates. Now, if you go, and here this is still hardware design, at the hardware design point of view, if you go one step in again, how do you, one step below logic gates is what electronic component do we find there? Anyone?
No, I don't remember. I think I'll have to revise this digital system first.
You find transistors. Because logic gates themselves are built up out of transistors. Agree?
Agreed. Yes, sir. Yes.
Okay. So now, let's say in the case of a NOR gate, it means X equals to A, two inputs that are inverted like that. added then inverted. Okay, so if you go, I mean, yeah. How would you implement a NOR gate with a transistor? That's also, it's an electronic circuit basically, using a transistor as a switch. If you go with the inversion part, meaning the NOT part, you would have the transistor as a switch controlled from its base. You have a pull-up resistor on the collector. Sorry, on the collector. Pulled up to VCC. You have ground and you've got the output here. So that will be your typical NOT gate. Because if you've got 5 volt there, let's say VCC is 5 volt. If you've got 5 volt there, there will be enough current, IB current flowing through the base resistor, which will make this transistor behave like a closed switch, in which case, when it behaves like a closed switch, this point will be pulled to ground. So you get a logic 0 there. That's why you go from 1 to 0. So it's an inverter. The same way, if you apply 0 volt there, this transistor is used in saturation, of course. There will be not enough current to switch it on, and it will behave like a fully open switch, in which case the 5 volts that is there, 5 volt that is there will be divided, will be split between RC, and an open circuit is modeled mathematically as infinite ohms, because remember, resistance is resistance by definition. Electrical resistance is resistance to current flow. Now, on an open circuit, there's no current at all that can go through, which means that it's maximum resistance to current flow. Hence, we model an open circuit by means of an infinite ohm. You'll model it as infinite ohms, which means the voltage that comes out here is a voltage divider between these two. Between RC and infinite will take everything basically. So you'll end up with 5 volt there when the input is 0. So that's a typical example of how a NOT gate or an inverter is implemented at the transistor level. And of course, you can have a transistor circuit for an AND gate, for an OR gate, for a NAND gate, etc. Okay, I just gave the example of an inverter. Then hardware design wise, one layer down the transistor, what do you get? It's long souvenirs, eh? Are you guys there?
Yeah, I'm here.
Yes,
what is the one layer below a transistor hardware design at the hardware design point of view?
Semiconductor.
Semiconductor is the layer after that. Normally here it will be a PN junction. Remember this?
I remember the word PN junction.
Yeah. And in a transistor, you've got 2 of them. You've got an EBJ junction, emitter base junction, and a collector base junction. So yeah, because PN junction is also known as a diode. Because from the base, let's say NPN in this case, from the base to the collector, you're actually having a diode in reality. And from the base to the emitter, you're also having another diode. In the case of an NPN, it will be like that. In a PNP, it will be the other way around. Meaning you have a diode facing the other way around. So that's one layer hardware design point of view of a memory cell. If you go one step down the PN junction, that is where you get your N-type and P-type semiconductors, meaning your silicon or germanium or even carbon is a semiconductor as well. And N-type and P-type are obtained through doping, of course. Doping of what? Of pure semiconductors. That, of course, now we are out of electronics and hardware design. Now we're talking about physics at this layer. And below that is mining, how they mine silicon and all of that. But the point is, to move from pure semiconductor to N-type, the process there is what we call doping process. We dope the pure semiconductors by adding some impurity atoms to it to produce the N-type of P or P-type semiconductor. So that's more or less when you hold the memory device in your hand, a RAM specifically, that is exactly the depth in terms of hardware design we're talking about here. For 1 bit, I'm not talking about megabytes. So you follow?
Yeah, no, I follow.
That's 1 bit of RAM. Because ROM follows a different design. When it comes to ROM, one bit of ROM or flash being the most popular one. There are many techniques, but flash is the most popular one. It's built up of a FET, a field effect transistor. Let me just recall the circuit. And you also learn this. In Digital Systems 1 in this case. It's clearly the circuit of one memory cell of 1 bit of a flash memory is shown in your Digital Systems 1 book. I just trying to remember it. Flash memory cell circuit. You guys use Floyd as well. Digital fundamentals. Agree? Check it. It's stuck or what? Yeah, you had a floating gate. It's exactly that. Memory cell. Let me see. Flash memory. Yeah, it's based on FETs where you've got a floating gate. The drain and the source used in conjunction to make up a memory of 1 bit. Let me just see. So what happens is that you apply depending on what is applied on the gates of the FET, you end up burning a logic 1 or a logic 0 on it. Because remember with ROM, even if power is gone, it must still be able to retain the logic bit, in this case, that you've saved on it. Make sense? Okay, I'll find the circuit from Floyd and textbook and actually explain it. But it's quite self-explanatory, is that, and there are many ways to burn I'm saying burn because that's how it used to be done in the past. You would burn data onto memory, as we call. Like with CDs, you burn data onto memory. With UV, with some initial PROMs, early age PROMs, programmable read-only memories. You do that by means of ultraviolet light, and you'll erase it with ultraviolet light as well because it's a permanent connection. Make sense?
Yes, sir.
Yeah, that's flash memory cell. Yeah, I just got it. But it's quite a basic circuit. Just wanna see, but it wants me to download it. Come on. It's gonna show. It's still loading. Remember this book? The raw address I was talking about, memory array, address bus, data bus. Agree?
Yes.
Step there. The memory cell for ROM. Let's see if I can get it. Oops, this is too much now. Yeah, but I still have the book somewhere. Let me see if I can get it. If this doesn't work, then we move on. Okay, this is too much now. All right. No, I don't want to sign up. Yeah, so it's flash memory cell. That's how it's labeled in the book. I think I have the book in the house. That is where I was. Chapter 10. Anyway, yeah, it uses a MOS transistor. Let's see. So it's a MOSFET with a floating gate at the end of the day. It's a MOSFET with a floating gate. Now, you understand what I mean by floating gate? A floating gate is basically a gate that's not connected to, not pulled high, not pulled low. So it's floating. It can take, which means it can take more or less any state. There we go. Flash memories, yes. That's the principle of how we store a logic 1 and a logic 0 when it comes to ROM. Yeah, let's see it now. There. Yeah. So we've got a floating gate. So flash memories are high density read-write memories that are non-volatile. They have the ability to retain charge for years with no applied power. Hence they are ROM memories. Flash memory uses a MOS transistor, meaning a MOSFET, with a floating gate as a basic storage cell. That's what is used to store a logic 0 or logic 1. The floating gate can store charge logic 0 when a positive voltage is applied to its control gate. So if we apply on the control gate, remember a MOSFET is good. Did you do any MOSFETs anywhere? No. In computer systems, you don't go as far as studying MOSFETs.
Nope.
You just do BJTs.
I've heard that word before. I've heard that MOSFET word before, but I don't know if it was at school or somewhere.
Yeah, okay. So it's the alternative form of a transistor. So you know of BJTs, obviously, because you do electronics 1 and 2. But it's another type of transistor whereby instead of having base, emitter, and collector, you've got gate, drain, and source. You get the point, but it's more or less the same principle, to the difference that in a BJT, it is current controlled. It's all about how much IBs we get on the input that it behaves. Either as a closed switch in saturation, open switch in cutoff, or active mode if it's more or less in between, not fully open, not fully closed, in which case it's used as an amplifier. But when it comes to MOSFET, they are voltage controlled. So it's all about how much voltage you apply from the gate to source. That determines whether it's going to behave like a closed switch, an open switch, or an amplifier. That's the only difference, basically. Yeah. So to design a 1-bit flash memory cell, we use MOSFET, and there's a specific reason for that, is that MOSFETs are voltage controlled. So you'd apply a logic 1, for example, on the control gate. When I speak control gate, I mean the gate. If you apply a high voltage there on the control gate, with little or no charge, the cell stores a logic 1. Why is it going to store a logic 1? Is that you apply a logic 1 on the gate, which means you apply 5 volt. Let's look at the logic quickly. You apply, let's say, 5 volt, which is logic 1 in TTL, or 3.3 in CMOS technologies. So now that means plus the gate is now of the gate, okay. For you to understand this, you need to go back to the actual semiconductor design of this FET, which is similar to the one of a BJT. Sorry, where is this from now? I don't want this. Okay, so if you look at the FET yeah, because the same way we've got NPN and PNP, in FETs we've got N type and P FET and N channel and P channel. Okay, but the point is, what will happen is that we've got a depletion region. So when you apply 5 volt, charges of opposite sides will repel. So what happens there is that when you apply 5 volt at the gate, that 5 volt will repel all the electrons that were sitting in this region, in the channel as we call it, the N channel. We repel the electrons in the N channel, and as they get repelled, the channel will become more filled with more holes than electrons. You agree? Because initially electrons are inside holes within the channel. So when you apply 5 volt on the N channel type of MOSFET, the plus of the 5 volt will repel all the charges of opposite sign attract. What am I talking about? When you apply 5 volt on this from gate to source, the source side is negatively charged, and it's negatively charged. The gate size is positively charged. The positively charged gate will attract, because charges of opposite sign attract. It will attract the electrons in the channel, and the electrons in the channel will be attracted towards the gate. They will form around the gate. The same way, the electrons, the negative side of the supply being on the source, it will attract also some more electrons in the channel, which will also form around the source. But the point in the end is that the channel, which is the region between the gate, the source, and the drain, will end up becoming depleted of its electrons, because they've all been attracted here and there, and will be having more holes than electrons, which means it will become positively charged. And if the voltage is strong enough, of which 5 volt is, it will be made up of holes only, to an extent that it will be charged positively, and we will say that it's storing a 1. Is that okay? So if the channel is made up of more holes than electrons, it's storing a 1. When the channel is made up of more electrons than holes, it's charged with a 0. And that happens when you apply a logic 0 at the gate. If you apply a 0 at the logic gate, at the control gate, meaning you connect that to ground, then what you're doing is that charges of opposite sign repel, minus and positive, the gate which is P by nature, in this case of an N-channel MOSFET, the minus and plus will repel. So what will happen is that the holes are the ones that will be repelled, and in the channel will end up with more electrons than holes, which makes the overall cell be negatively charged, and that's how we store a 0. That's the logic there. Okay, so that's when it comes to the design of ROM and one cell of ROM. And then you can think now, you can scale it up and think of how you'll design a USB of 1 gigabyte and so on. You'll go from these cells, you'll know what is your web length, and in the end, it's like a matrix of these. Is that okay? That's clear in terms of memory, I hope. And how memory is designed all the way down to the hardware that goes with. The hardware design of memory, basically. Okay, so those are that's the model we use to model a computer system. Now, in terms of architecture components, the elements that define the architecture of a computer system are the hardware, of course, the software, data, and communication. So when you speak about the architecture of a computer system, you need to define what hardware it's made of, what software runs on it or it can handle, what type of data does it deal with? Is it images? Is it sound? Is it, is it text? Is it characters? And what type of communication abilities it has? Okay, that's important. Now, in terms of our input-output devices, hardware component, the hardware part, we start with the hardware part. It's made up of input-output devices. The storage devices are seen as hardware. Memory, as we just explained it, as you can see, it's hardware. Hence, we dived into a lot of electronics. Of course, the CPU itself is hardware. It's made up of an ALU and a control unit, and finally an interface unit as well. Memory is definitely hardware. Okay. And it's memory, if it RAM, it's short-term storage for CPU calculation. So a CPU is performing calculations on variables. These variables are stored in RAM as temporary storage, and the result of the calculation of computation is also loaded most of times either in ROM, most of times in RAM, but sometimes in ROM as well if it's a result that needs to be stored permanently. Now, what are the typical personal computer systems? Well, a typical personal computer system, this is more personal, as the keyword says. This is more old style because nowadays we have different setups, but you would at least have a CPU with memory and I/O interface. And in terms of peripherals, you would have some input peripherals you need for a personal computer, a keyboard. A floppy disk is no longer applicable, that's old. So you'd substitute that with a USB port, for example. You've got some communication interface, you've got a hard disk, of course, you might have a printer interface, a mouse, a speaker. So yeah, that slide is kind of outdated. When it comes to the CPU, is made up of an ALU, as we mentioned, arithmetic logic unit, which performs arithmetic and Boolean logic calculations. The control unit, what is the purpose of it? It controls processing of instructions, controls movement of data within the CPU. The interface unit moves instructions and data between the CPU and other hardware components. Other hardware components, of course, which involve memory, which involves the I/O devices, etc. So it's thanks to the interface unit that movement is possible. So now, what is the core element of that makes up an interface unit? You cannot speak about interface unit without speaking about a bus. And a bus, by definition, by basic definition, a bus is a set of wires. A bus is a set of wires. That is by pure definition. But of course, within a microcontroller, within a computer, a personal computer, you don't have wires per se. You can also see it then as a set of tracks. And when I say tracks, these are copper tracks on a PC board, which is another alternative for wires, basically. Okay, but they are etched on the PC board. So that is what we call a bus by definition. But we've got different types of buses now. We obviously have, so it's a bundle of wires that carries signals and power between different components, hardware components. We've got now different types of buses, as you know. You've got the address bus, you've got the data bus, which are two different buses in the Harvard architecture. But when it comes to von Neumann, which is the alternative, in the von Neumann architecture philosophy, one bus is shared by data and address. But in general, in Harvard architecture, which is the most popular architecture used by most computer systems, the bus, we've got a separate data bus. We've got a data bus which is separate from the address bus. Okay. Beside those two buses, we also have what we call a control bus, whereby control signals are carried. and we finally have what we call a system bus. So we've got 4 types of buses. The system bus is the bus that manages communication between memory and the CPU for all type of system calls that we can get within a computer system, either initiated by an operating system if we are in a case of any computer system that requires an operating system, or even by firmware in the case of a microcontroller. Okay, memory, we've discussed the concept of memory. RAM memory is called primary storage because it's the layer of memory that is closest to the CPU. It's for temporary storage and the CPU interacts with it all the time. We have explained the memory size, okay? The purpose of memory is obviously to hold both program and data, that we've said already as well. Yeah, we'll go to the software component just now. Yeah, so now remember we said at an architecture point of view, a computer is made up of hardware. We've described hardware quite a lot today. We've got the software component, we've got memory, we've got software component, and we've got communication. Now we're talking about the software component. You can't speak about a computer system without having a software component. And when it comes to the software component of a computer system, for us to understand it, we need to go all the way down from hardware, because at the end of the day, the software, which is at the user level, which we call application programs in any case. So these are your calculator, Outlook, etc., and many other that we can develop, must be able to make use of the hardware available on the computer to achieve its purpose. So what are the different software layers that are in between? So from the user point of view, the software application that is closest to the user is what we call application programs. One layer down, we've got the user interface. That will be your user interface type of applications. That will be your that can be provided in many ways. That can be provided in terms of well, user interface can be provided in terms of a text box, in terms of a text box, meaning a user will have to put text into it. Can be provided in terms of an of a microphone, in which case the user will software that handles the function of a microphone, which means in that case the user will provide data in form of sound. You know, that's the user interface layer. So there we're talking about, we're mostly talking about your type of socket programming, etc. So one layer below, we've got what we call API, Application Programming Interface, which serves as interface between the operating system basically and the upper layers of software, which are user interface and application programs. Application programs can talk directly to APIs, which provide an interface to the operating system. Okay, of course, file management system manages files, kernel. The file management system and the kernel form the basic operating system part. But the operating system can have more than the file management system and the kernel. It could also be made up, because the purpose of the operating system, of course, is to manage operations, meaning manage resources on a computer. So the kernel is very important with that respect. The file management system, among the resources being managed, exists what we call files. In the case where the data is organized in terms of files on that specific computer system, of which on a microcontroller we can do file systems, but most of the times we use lower data types such as integers, floats, etc. So that those two there represent the operating system basically, together with the drivers. File management system and kernel, sorry. But below the file management system and kernel, we've got drivers, which are firmwares actually. Drivers are firmwares that manage the actual hardware. So you have got a USB driver, you've got a Ethernet port driver, So that's the lowest level of software you get in a computer system. Okay. Yeah, the kernel does, of course, memory management, resource scheduling, program communication. It has to, that's the operating system basically. So it has to handle all sort of conflicts in terms of access to shared resources, maybe two processes trying to access the same memory, or yeah, writing to it or reading from it. So those type of conflicts are all managed by the kernel within the operating system. Okay. That's more or less the diagram of the software component within a computer system. I'll be back just now for us to finalize with the other 4 slides. We can resume at 15 past. Just another short break.
Sorry, sir.
Is that okay?
Yeah, before
yes,
you
go
go
ahead.
I don't want to forget the what do you call it? My questions, right? So I've got 2 questions. Number one, right? This theory that I see here, the software component, when we come to exams, how are we gonna be applying it, or how are we gonna be tested on it?
Okay, that's a very good question. The theory that so the assessment method is mostly of an applied kind. So I would not, okay. I will not ask you explicitly to reproduce this diagram, for example, but I'll give you a case scenario in which case you will have to know the diagram and then identify what each block represents in terms of that case scenario. That makes sense?
Yeah, it makes sense. And then another thing, which material can we use just to catch up with the subject?
Okay, to catch up with all stuff, and you shouldn't worry about a lot about that. You'll catch up. I'll provide one book I think solves everything. It's called Digital Fundamentals. It's the book they use for Digital Systems 1. And I'll give you exact pointers to which chapters you can look at. Because what you catch up with, basically, you're just catching up with basics of digital systems.
Okay, and then the slides, we're also going to get them, right?
Of course. You get the book, you get the slide, the study guide, and everything.
Thank you. Thank you, sir.
Okay, so I'll be back just now for us to finalize with the 4 slides remaining.
You said okay? What, at quarter past?
Yeah, quarter past, just now.
Okay. Thank you.
Okay. Sorry, it took a bit longer. We can carry on. So that's the software component. In terms of the communication component is comprised of a computer system comprises of both hardware and software, of course. Okay. Hardware, the communication component, which is next, comprises of both software and hardware. Of course, as you know very well. On the hardware side, you've got your communication channels, which could be physical connections between two computers. That will be the case of phone lines, optical fibers, wire cables, infrared lights, radio waves could make up the channel. So that's the medium through which data is transferred from one point to another. And it's made up, of course, of interface hardwares as well, which handles communication between the computer and the communication channel. So these are your modems and network interface cards. Okay. Now, so for example, for Wi-Fi, you need a Wi-Fi modem, which we also, so modem is actually the same thing as network interface card. And the modem will be made up, of course, of modem stands for modulator, demodulator. So the purpose of a modem is to, okay, during transmission, it modulates. So you have, what does it mean modulating? Let's say one wants to send a message, hello. Types it on a keyboard, it's passed on to the CPU. The CPU realizes that it's for sending, it sends it to through the whole software channel, from all the way from application layer to through the API, all the way through the operating system kernel, all the way down. And when it gets to the modem, it's modulated during transmission, meaning maybe that's too much even. Let me take the letter A itself, the character A. If you look at it ASCII code, character A is, what is the ASCII of A? Capital A. Let me look at the ASCII table. I wonder why it's taking forever. Yeah, so let's just take H because part of the hello we're about to look at. H sits at 72 in decimal. In hexadecimal is 48. So that is the value that ends up on the modem. So it comes as OX 48 in hexadecimal. So in binary, we're talking about 0, 1, 0, 0, that is 4. Then 8 is 1, 0, 0, 0 in binary. So that is the data that gets to the modem. Modulation means what? Means we need to send this data, but we have an oscillator. Let's say Wi-Fi through the Wi-Fi, and as you know very well, when it comes to the Wi-Fi, can you guys still hear me?
Yeah,
Yes,
yeah, I can hear you.
Yes, we can. Okay, now we can't hear you anymore.
I say we can't hear you anymore.
What about now?
Yeah,
Say
now
something
I can
again.
hear you.
Is it better now?
Yeah.
Okay, so I was explaining that A or H, sorry, typed on the keyboard, filtered through all the software layers, all the way down to the modem, arrives as an ASCII code 48. 8, which in binary value gives that. Now, this is what needs to be sent out through Wi-Fi, for example. When it comes to Wi-Fi, we know we've got two types of Wi-Fi, 2.4 gigahertz, and we've got 5 gigahertz Wi-Fi. So now, that high frequency, because this is wireless communication, this much high frequency is needed to send this message so that it can travel far through electromagnetic waves. So you'll then need, okay, first of all, there will be what we call an oscillator circuit, of which the purpose of it is to produce a sine wave, a sinusoidal signal at the modulating frequency. So now there are many types of modulation. You can do amplitude modulation or frequency modulation. That's not the point of this subject. But the point is, we will have modulating means we'll have to capture zero. Zero is like the content of it's like the mail, the later, for example. And the signal from the oscillator is what we call, it's more like the envelope. So we'll envelope zero into the carrier. This is what we call the carrier signal. Into the carrier for this carrier to carry it over the air. So that is that process of enveloping the data into the carrier signal is what we call modulation. So that's modulation. And that's handled by a hardware device, which in the end, once modulated, is given to an antenna, and from the antenna it's radiated over the air and sent to wherever it's supposed to be sent. Now, during reception, the modem behaves like a demodulator. So the signal was carried inside there, enveloped inside the carrier, these values here, depending on the logic at which we are, and many other modulation techniques. Now, on the demodulation side, during reception, the same modem, because it's supposed to still be able to detect incoming emails and all of that, when an email comes, it will demodulate it from the envelope, meaning removing the message from the envelope. And as it removes it from the envelope, it retrieves what the message is, and it can pass it across all the way to the application layer, whereby we've got Outlook maybe, and it will pop up to say there's a new email. You get the idea there?
Yes, sir.
That's
so
why
basically data transmission in the wireless space, right? So
Yeah,
I have a question.
Go ahead.
I guess the difference between the 2.4 gigahertz and the 5 gigahertz would be that the range probably from the 2.4 gigahertz will travel further than the 5 gigahertz, because the higher the frequency, the less the coverage.
Okay, yeah, that's a good question. When it comes to the higher the frequency, the faster the signal.
But the less the coverage.
Faster doesn't mean further.
Yes,
faster.
exactly.
Faster, yes, because that's why we're talking about with 5G, for example. Now
yes.
we are we're managing to get gigabits per second of speed, because we managed to tap into the range of 50 gigahertz.
Yes.
But the signal that goes far is definitely, as you just mentioned, it will be the lower frequency one, but it will be slower than the 5 gigahertz one.
Yes, yes. So, hence, with 5G, they'll have a home module and they'll have a microwave outside to receive the signal, right?
Yes.
Okay, thanks.
So that's the concept of modem, and the modem is not only for how do you call it, for Wi-Fi. Modem is a general thing for most communications that computing systems deal with, including Bluetooth. For example, you need a Bluetooth modem within your computer. Infrared, you'll need an infrared modem, etc. So that's the concept of modem as a hardware component of the communication part of a computer system. But communication also involves software, and software is the implementation most of times of what we call network protocols. Okay. Okay, so now we haven't spoken about the data aspect, which is the remaining component of a computer system. But all computer systems, no matter how complex they are, must at least have a CPU, memory, I/O devices, and some long-term storage. That's the minimum requirement for a computer system. I'm trying to admit someone. The minimum requirement for a computer system will be those four. Hello? Yeah.
Oh, sorry for going in and out. So, like my audio was not working.
Okay, it's okay. So now, besides because we mentioned protocols, which are the software component of the communication part of a computer system, protocols are very important because they play a very important role in computer systems, because they create standardization. So they create a common ground rules of communication between computers, because point is, modern computing does not work standalone. In modern computing system, computers are networked. They talk to each other. So that way protocols become very important. It was very important to define some common ground rules that will allow computers to talk to each other. And that is implemented by means of protocols, which are the software component of communication part of a computer system. And there are many protocols we know of. For the web, for example, web servers and web browsers are interlinked by HTTP links. TCP/IP links is the protocol used for the internet to connect any computer to the internet and local area networks. We've got ATAP between, for example, CPUs and CD-ROMs, and all the way to UART, serial communication, I2C, SPIs. All of these protocols are very important in computer systems. Now, when it comes to standards, which is the concept of standards in computer systems is directly linked to the concept of protocols, with a bit of nuance, in a sense that standards are created to ensure universal compatibility. Standards go a bit it's a much broader concept than just protocol, in the sense that standards are also applicable to hardware. Okay, and mostly are created by means of a committee, which normally sits and decide on standards. When it comes to electrical standards, the biggest governing body is what we call IEC, right? And we've got many computer societies that define standards. Okay. Now, standards are applicable to all aspects. They're applicable to hardware, they're applicable to software, they're applicable even to data, because it's thanks to standard that we are capable to classify data as, let's say, image data as MPEG, video data as MPEG, or image data as JPEG or GIF. That is a standard of data. So there's a standard for hardware, for software, for data, and even for communication. But when you speak protocol, is mostly applicable to communication only. I won't go into the history, but when it comes to history of computing, it's traced back that all this type of computing device was invented by Blaise Pascal, and that was more of a calculating machine, more of a calculator. And from there on, we went to punch cards, and we slowly got the Boolean logic and programming languages, and leading to the computer the way we know them nowadays. So that is the introductory slides for, those are the introductory slides for the hardware design subject, and looking forward to have a good semester with you guys. I'll share the material as I promised. I'll let you now go to the other classes so that you're not late. Is that okay?
That's okay,
Yeah,
sir. Thank you so
that's
much.
fine.
Sure. I'll also share the recording, of course.
Okay. So when do you think you'll share the study guides and everything? You said today, right?
Yes. Latest really
Okay.
will be, because I know you guys are working, so I want you to have to look at it before you go back to work. So I'll try.
How many?
If I fail today, it will be tomorrow, though.
Okay. How many are we in the class so far?
According to my list, 5.
5. Okay. So at least it's going to be easier for you to give us that focused sort of.
Absolutely. My aim is actually to make sure you both pass. I don't want anyone to fail. It would be ridiculous.
Yes. Yeah, I agree. Yeah.
I have, you are just few, so I will give you the best attention possible.
I agree. Thank you so much, sir.
You just have to cooperate at the end of the day.
Yeah, I think the study guide, even especially for guys like us who are working, we need to even during the week try to prepare before your classes to catch up with some of the concepts that we had maybe missed from the past. Yeah,
makes sense. Okay, I'll see you guys.
Right, thanks, sir.
Sure.